we recording?
All right, we're recording. Sorry about that. Let's get ready to OChem. Woo! Friday afternoon. Woo! All right, so we're going to pick up where we left off in class, intermolecular versus intramolecular reactions. I've already preloaded a whole bunch of stuff drawn on the little whiteboard. So pause is going to be your friend. I've got 9 slides already ready to go here. So we're gonna make it for lost time here. All right. So try to go with the theme of red and blue today, because Captain America drops tonight. That's where I'm hopefully going to be after all this. All right. So we left off intermolecular reactions. 2 molecules become 1. Right. So that's right down here. Right. You've got 2 molecules here, a nucleophile and an electrophile. If you remember, nitrogen is partially negatively charged. This carbon here is partially positive. Right? It's electrophilic. It wants electrons. So then the nucleophile attacks that, and you get 1 new molecule. So you have 2 molecules become 1. Intramolecular reactions, 1 molecule becomes a ring. Right? So up here, where you have your nucleophile and your electrophile in the same molecule. Now, if you look, the oxygen right here is 1, 2, 3, 4, 5 atoms away. So you just make a 5-membered ring. So oxygen is 1, 2, 3, 4, 5. So all you need to do is count from your nucleophile, whatever's bonded to the metal, remember, plus, minus, to the carbon that has your leading group, that has your halide. And that will tell you how big the ring is. And if you number everything, you can then see, all right, carbon 3 has 2 methyl groups. Well then, carbon 3 over here, so I got 2 methyl groups on this carbon, I have to have 2 methyl groups over here. Right? So how do you make your nucleophile in your molecule? You typically do that with an acid-base reaction. So OH is a weak acid, but an acid nonetheless. All right? You can have a base like sodium hydride that will come through, pick off that proton, and make your alkoxide. Right? Or you can simply just use sodium metal and end up making your alkoxide that way. So for example, you could just have your alcohol and your halide hanging out. So here's your alcohol, here's your halide. You add sodium hydride, that turns OH into, start down here, NaO. Right, so then that makes your alkoxide. So this is the sodium hydride. And then that will cause it to cyclize. So again, like we did before, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that will get you your product. Okay. Now, let me switch slides here. All right. So, in general, an intramolecular reaction will happen more quickly than an intermolecular reaction. So it makes sense, right? If the nucleophile and the electrophile are held together in the same molecule, the odds of them finding each other quickly go up, right? If you have the nucleophile and electrophile are in different molecules, they can be clear on the other sides of the country and never come together, or take a long time to find one another. So being tied together in the same molecule makes you go faster. Concentration also plays a role. Low concentrations favor intramolecular reactions, high concentrations favor intermolecular reactions. back over to my little thing here. Okay, so at low concentrations, it's less likely that you're going to bump into another molecule. So again, if your electrophile and your nucleophile are in the same molecule, you don't want your electrophile bumping into a nucleophile for another molecule. You just want it to be in the molecule that you have and stick together. That's right. And stick together. Right? So at low concentration, you're less likely to run into another molecule. Conversely, at high concentration in an intermolecular reaction, you need your nucleophile to run into an electrophile it's not bonded to. So you want to increase the chance of those two molecules finding each other. So you have a higher concentration. Right? So at a higher concentration, this increases the odds of two molecules meeting. So think about it like this. Say you live in Wyoming. There's like 5 people in Wyoming. You're single in Wyoming. The odds of you finding someone to date, very low. Right? That's a low concentration of people. You're going to react with yourself. Take that for what you will. Right? Now you live in New York City. There's like 5 million people in New York City. The odds of you finding someone, meeting up with someone, go up. Right? So low concentration, you're alone forever and ever. High concentration, hey, you're going to run into people, you're going to meet people, you'll have friends. Right? So intramolecular reactions, low concentration, high concentration, intermolecular reactions. I kind of got depressing there, but whatever. All right. So you going here. Okay. Ring size plays a role in if a reaction is going to be inter or intramolecular. So if you're forming a 5, 6, or a 3-membered ring, that reaction will go forward in an intramolecular fashion. If you're making a 4, 7, or larger ring, it's going to prefer to be intermolecular. So what am I talking about? Oops. Sorry, guys and gals. All right. So if you're going to make one of these rings, right? We'll throw an oxygen in there, make it look kind of like what we were saying before. Right. So if you're going to make a 3, 5, or a 6-membered ring as your product, that reaction will occur. If you're going to make a 4, 7, or 8-membered ring, that reaction is really slow and would prefer to then do an intermolecular reaction. Right? So even regardless of the concentration, if you're going to make a small ring, if you're going to go from here to that small ring, this is really slow. This is the intermolecular reaction. It's really slow. And so what happens is, as opposed to it making the ring, it will actually it'll do the intermolecular reaction, and it'll actually just stick 2 of these guys together. So you'll have the sodium hydride. Oops. Ad-libbing here, and now I'm totally screwing stuff up. All right. Right? And instead of 1, 2, 3, 4. So instead of doing that and going here, that's too slow. And so what will happen is it will just react with another molecule of itself to make this product. But so making a 4-membered ring and a 7-membered ring, you just can't do. You really need to go, you can make 3, 5, and 6-membered rings this way, but you can't make, 3, 5, 6 you can make this way. 4 and 7 you can't, or larger. So whenever you go to make a 4-membered ring or a 7-membered ring, it will just rather stick 2 molecules together. All right, so let's talk about the mechanism. So we're through SN2 reactions. Done. You got all that in your head, right? SN2 reactions, polar aprotic solvents, primary and secondary halides, and charged nucleophiles. Know it, love it. Right, now we're going to talk about SN1 reactions. You're going to need to be able to differentiate an SN1 reaction from an SN2 reaction. Right? So, first let's talk about the name. Right? Oh, technology is totally owning me. Sorry. All right, so SN1. Right? The S is for substitution, the N is for nucleophilic, and the 1 is for unimolecular. Right? So just like the SN2 reaction, does it make a whole lot of sense? Isn't that right? So so it's SN1, but it is a two-step mechanism at its simplest base level. It's 2 steps. Right? So SN2 was 1 step. SN1 is 2 steps. Right? But this comes from the rate law, right? So being unimolecular means that the concentration of only one compound determines the rate of the reaction. So it doesn't matter how much nucleophile you add to your reaction. All that matters is the concentration of your alkyl halide. Try to do sound effects too, right? So the rate law is some constant K times the alkyl halide, right? The alkyl halide is all that matters. You don't care about your nucleophile at all. Right? Adding more nucleophile does not affect the rate. Right? So, for example, kind of like we did for SN2 reactions, if you have a rate of 1, when your alkyl halide is 1 and your nucleophile is 1, right? We can then extrapolate. So what's your rate if your alkyl halide is 1 and the concentration of your nucleophile is 10? Well, nucleophile is not in your rate law. So I can make nucleophile a bajillion. But all that matters is the concentration of the alkyl halide. So alkyl halide is still 1, rate's still 1. I could go 3.5. All that matters is alkyl halide. 3. Right? It doesn't matter what the nucleophile concentration is at all, because it's not found in the rate law. All right, let me switch slides here. There we go. All right. So, no, we'll go this way. Sorry, guys. Let's figure it out. Okay. So the rate of SN1 reactions is exactly the opposite of the rate of SN2 reactions. Right? So for SN1, tertiary halides are fastest. Then secondary halides, primary halides, and methyl halides. And I've got a, I don't know, Bordeaux electronic typo. There we go. Primary and methyl halides never undergo SN1 reactions. SN1 reactions can only occur with tertiary and secondary halides. And this is a result of mechanism. Right, so I think on the slides, as you take away carbons and replace them with hydrogens, right? So this carbon goes away, add a hydrogen, reaction gets a little slower. This carbon goes away, add another hydrogen, reaction gets slower, and then finally I get rid of my last carbon, I have 3 hydrogens, super slow for SN1. Right? And the reason comes down to the mechanism. Right. This is the last prep slide I have. Now we're just going to go a little crazy, right? So the mechanism, your leaving group, your halide leaves. Peace out. It goes away. Right? And then you generate a, as we've seen before, carbocation. Right? And what are your carbocation stabilities? Tertiary carbocations are more stable than secondary, they're more stable than primary, more stable than methyl. Right? So cation stability, carbocation stability, right, is tertiary, then secondary, big gap, primary, big gap, methyl, right? So the easier it is to make your carbocation, the more stable your carbocation is, the faster your reaction. Because the slow step in the reaction, the rate determining step, is the generation of your carbocation. Right? Once you have that carbocation, your nucleophile will add to it like that. It'll add really quickly. Right? As soon as it sees a carbocation, nucleophile is like, bam, I'm on it. Right? Now, so let's do like kind of a real mechanism here. Right? You got your leaving group that leaves, right? So bromine leaves, you get your carbocation. Your nucleophile, in this case water, adds. And then, just like in our other mechanisms that we had, like with hydration and stuff from alkene reactions, water comes in with 2 hydrogens. That means the oxygen that you added is going to have 2 hydrogens and a positive charge. Remember, oxygen with 3 bonds equals positive charge. And then you have to use another molecule of water, in this case, to remove your extra proton. Right? So we can turn this around as well. So let's say you had some secondary alcohol, and we treated that with HBr, right? So lone pairs of oxygen are basic. They can reach out and grab that proton. It's protonated, right? So OH, bad leaving group. Water, good leaving group. So by adding that proton, we went from a bad leaving group to a good leaving group. That allows proton to leave, water to leave. You get your carbocation. Right? When I push the electrons on the bromine, I made Br minus. Then that Br minus can come in, blank and blam, attack the secondary carbocation, and give you the product. Right? But again, the slow step, this is slow. But look at the blam, so that's fast. All right? Get moving here. All right, so we went over this a second ago. Tertiary, secondary, primary, methyl. Right? If you draw a mechanism for an SN1 reaction that has a primary or methyl carbocation, you are wrong. Start over. So you will never make a primary or a methyl carbocation for an SN2 reaction, an SN1 reaction. All right. Now, with the stereochemistry for SN1 and SN2 are different. SN2, you have to invert your stereochemistry. An up leaving group becomes a back nucleophile. Right? Really straightforward. So for SN2, right, and up leaving group, right, an up halide reacts with the nucleophile to give you a back nucleophile, and vice versa. For SN1, an up leaving group, right? Now, nucleophiles in nucleophiles in SN1 reactions aren't charged. They are neutral. They are weak nucleophiles. Right? You get this squiggly line. Right? That squiggly line is telling you there's a mixture there. There's a mixture of forward and back. So you end up making a racemic mixture. Right? The reason that you get this mixture, real quick, you can draw it like this, or I would accept just a straight line. Right? Just let me say there's no stereochemistry there. Right? So the reason you end up with a mixture in an SN1 reaction is because, remember, carbocations are flat, right? So let's say we've got this alkyl halide, and we lose bromine. I'm trying to draw this, right? Yep. What happens is that this alkyl halide will become flat. You have your positive charge. So you go from an sp3 hybridized carbon, which is tetrahedral, to an sp2 hybridized carbon, which is trigonal planar. Now, if you're the nucleophile, you have an equal chance to attack from the top or attack from the bottom. If you attack from the top, you make this an enantiomer. If you attack from the bottom, you make this an enantiomer. And again, they're kind of terrible. These are my dashes. I blame technology, but whatever. Okay. Same thing over here. I don't know why I have the eraser set on like Bigfoot, but whatever. Right? So these guys are enantiomers of one another. They're non-superimposable mirror images. Right? And you have an equal opportunity. So this is a 1-to-1 mixture, which means you end up with a racemic mixture. So since a carbocation is flat, you get a 1-to-1 mixture of possible products. So let's talk about leaving groups for SN1 reactions. Right. So the leaving group pattern is the same for the leaving group ability is the same for SN1 as it is for SN2. Right? So iodide is faster than bromide, is faster than chloride, is faster than fluoride. Right? So fast, right, fast, screw. Right? And this just goes back to what is best able to handle having that negative charge, right? Something that's small, doesn't have a lot of electrons, or something that has a ton of electrons and can take too long. So leaving group ability impacts, so the leaving group ability is exactly the same. As you go down the periodic table, you become a better leaving group. All right? SN1 reactions, like weak nucleophiles. Right? So that means, do they like alcohols? Amines of all various strengths, right? So primary amines, secondary amines, and ammonia all work. And whoop. And files. Right, this is where you gotta pause the video, boom, pause. And go look through your notes and where have you seen this collection of stuff before? Alcohol, the amines, the thiols, these are your polar protic solvents. Okay? So, many times the solvent and the nucleophile for an SN1 reaction are the same. Right? So, when a solvent is your nucleophile, it's called a solvolysis reaction because the solvent reacts with the electrophile. So, in an SN1 reaction, oftentimes you'll have, say, a secondary halide of some sort, and it can just be in alcohol. Right? These are conditions for an SN1 reaction. Secondary halide, weak nucleophile. So, blicky blam, bingo bango, they come together. That's a solvolysis reaction. The solvent is reacting to give you the product. So, secondary halide. Sure, yeah. We're not gonna try to break up with bromine a little bit. Well, maybe cheat on bromine. Get a little loving from iodide. What? Right? I can use a thiol. Right? Stinky reaction, but no problemo. So if you're So then again, you have weak nucleophile, and it's also a polar protic solvent. You add that to your reaction. So you want to have, go back to red. You want to have, so you're going to ask me, what about a ring? A ring ain't no thing. Right? Again, apply the same rules. Different structure, same rules. Right? So, take a secondary amine. Redraw your oh my gosh, I meant to think blue. Love of God. I'm going colorblind up here. All right. Boom. Right? So your amine always has to have a hydrogen. If you don't have a hydrogen on your amine, it's a no-go. So you have to use ammonia, primary or secondary amines. Okay? So, and again, if you have a chiral, if you have a chiral halide, doesn't really matter what you add. All right, again, polar protic solvent / weak nucleophile. You're going to do SN1. There you go. Oh, wait. I actually screwed up, guys. Somebody yell at me. Somebody right now is screaming at their computer. Right? So this is SN1. You lose stereochemistry. Right, your stereochemistry just peace out, it's gone. Alright. Now I'm not gonna like beat your heads against this, I expect you to know it from earlier, but SN1 reactions go through carbocations. And if you remember, anytime you see a carbocation in a mechanism, you have to be able to do a rearrangement. So you need to make sure that if you have something like this and you treat it with water, right? And you would get this product. Again, the question is, what happened? I had this down, and you wouldn't ruin my life. I know, it's a roll. Right? So remember the mechanism. Bromine leaves. Now you get, oops. Oh, no. Shoot for a small eraser here. There we go. Right. Bromine leaves. You generate a carbocation. Right? Whenever you have a carbocation, you have to stop and say, can I rearrange this? This is a secondary carbocation. There's a hydrogen right here. Right? So that hydrogen can come over. Whoop, and you can go from a secondary carbocation to a tertiary carbocation through a 1,2 hydride shift. And then from there, water adds. And again, don't forget, there's 2 steps. The water adds, and you have to come take off the extra proton. Right? So in SN1 reactions, you need to make sure that you account for the possibility of a carbocation rearrangement, just like you would in addition of HX to an alkene or hydration of an alkene. Right? It doesn't matter how you get to the carbocation, it still does what it does once you've made it. It doesn't matter how it got there. Right? So we've already touched on this a little bit. So SN1 reactions go best in polar solvents because carbocations are polar. So you need a polar solvent to stabilize your carbocation. SN2 reactions with charged nucleophiles go best in non-polar solvents. If we could do these reactions in hexane or benzene, something that is not polar at all, they go really fast. Right? Polar solvents stabilize the charge that you're making and slow down the reaction. Right? The problem is that last time I checked, you can't dissolve polar stuff in non-polar solvents. Right? Again, if you learn nothing from Gen Chem, likes like likes. Polar things dissolve in polar things. Right? So our trade-off is that we use polar aprotic solvents. So they're polar enough to dissolve the reagents, but they don't hydrogen bond and slow the reaction down. If you're using an uncharged nucleophile for an SN2 reaction, they work best in polar solvents. Right? For our purposes, we usually only deal with charged nucleophiles for SN2 reactions. Oh, excuse me. Right, so here's kind of the next big thing we have to be able to do. Choosing between SN1 and SN2 reactions. Okay, you're going to have to be able to do this for the test. So, SN1 reactions, they like low concentrations. So the lower the concentration, the more SN1 product you're going to get. They like poor nucleophiles, so things that are neutral. Water, alcohol, thiols, secondary amines, and primary amines. Right? And they like polar solvent. They like particularly polar protic solvents. Right? SN2 reactions like high concentrations. They like strong charged nucleophiles. And they like polar aprotic solvents. Right? I can't, on an exam, like when I write a reaction up, convey to you how concentrated a reaction is. So what I need you to be able to do is the following. Is to look at a molecule or a reaction and tell me if it's going to be SN1 or SN2. Right, that's an F, sorry. I'm like having all kinds of problems with my little like magical pen here. All right. All right, so let's look at these, right? So I kind of approach this as a checklist. So step one, alkyl halide. Step two, nucleophile. Step three, solid. So if you work through step one, step two, step three, you can figure out what type of reaction it is. So for this one, step one, alkyl halide. Primary halide. Is it SN1 or SN2? It's SN2 because you should know, that SN1 reactions cannot happen with primary halides. With primary halides. Dear gosh. Right, so you know the product has to be, it has to be the SN2 product. Right? When we can work through this, nucleophile, step two, nucleophile is charged. Right? Nucleophile has a metal. If it's got a metal on it, it is going to be charged. Right? But in the solvent, THF is a polar aprotic solvent. Right? So these all things point to point to SN2. Again, step one, look at our halide. Right? This is a tertiary halide. You shouldn't have to go any further. Right? You know that SN2 reactions cannot occur at tertiary halides. So you know this has to be an SN1 reaction. Sure, this is SN2, right? There we go. Now kind of this last one. This is the step one, secondary halide. SN1 reactions can occur at secondary halides, and SN2 reactions can occur at secondary halides. All right, so step one doesn't tell us jack. Step one tells us we can do a reaction. Step two, let's look at the nucleophile. Here's our nucleophile. It has a metal. It's charged. Very charged nucleophile. Ding, 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 ding. That says SN2 reaction. Why is that important here? Because that tells us about the stereochemistry. Right? That tells us that the bromine is up. My nucleophile has to be back. Right? On the exam, what I do, because a lot of times the products are the same, SN1 or SN2, doesn't matter, is I give you a box. I'm like, bam, box. Right? Type of reaction. Got some boxes going on here. Right? And then give you some structures. And I give you some structures here. while I'm writing, you get your think on, get some learn on. Right? And so what I'll expect you to do, again, you hit pause, boom. All right, good? All right, so step one, work through the 3 steps. What type of halide do I have? Right, this halide is secondary, doesn't tell me anything. What's my nucleophile? It's uncharged, right? There's no charge, there's no metal, it's uncharged. So that must mean this is an SN1 reaction. So then what does that tell us about the product? Well, the fact that I can't draw the product, right? Everything comes along for the ride, right? And then no stereochemistry in my product. I get a racemic product. The stereochemistry is locked because I went through the flat carbocation. Come to the next one. Secondary halide again. Again, SN1 or SN2. Let's go to the next step. Let's look at our nucleophile. Oh, nucleophile is charged. It's got a metal in it, right? So that means charged nucleophile SN2. Boom. Right now. What does that tell us about our stereochemistry? Chloride is back. That means our nucleophile is going to be up. And again, bring everything along for the ride. I've got this isopropyl group here. I need to have that isopropyl group there. Right? Go to the next one. Secondary halide. Again, doesn't give us any information. Nucleophile, uncharged. That means SN1 in the hizzy. Whoop, whoop. Okay, so again, what does that tell us? That tells us that we have no stereochemistry on the product. Right, whenever you add one of these uncharged nucleophiles, just point this out, if I've got 2 hydrogens here, I'll only have 1 in the product. If I go back a slide here, right, I had 1 hydrogen here, I have no hydrogens on that nitrogen. Right, you always lose 1 hydrogen because that bond is given up to make the carbon nucleophile bond. Right, so you should be able to determine the difference between SN1 and SN2 based on the structure of the halide. Right, primary methyl, always SN2. Tertiary, always SN1. Secondary is the only one that there can be any confusion on. And then by looking at the nucleophile. Neutral nucleophile, SN1. Charged nucleophiles, strong nucleophiles, SN2. All right. So let's talk about how double bonds affect substitution reactions. Right, first we're going to talk about vinyl and aryl halides. These don't undergo SN1 and SN2 reactions. So, vinyl halide. Oh my gosh. Vinyl halide. Not a word. Come on, there we go. I still real good. All right. Vinyl halide. Can't do an SN2 reaction because your nucleophile doesn't want to approach, right? Pi bond, lots of electrons. So your nucleophile doesn't want to be part of that, right? So it can't do SN2 because you can't get backside attack. Backside attack is prohibited. because of all these electrons here. So all these electrons are here. They stop your nucleophile from approaching. SN can't write. SN1 is a no-go. Right? Because remember what we learned when we did alkyne chemistry? Right? Vinyl cations are bad. Right? Vinyl cations aren't stable. If you have a mechanism with a vinyl cation, you're wrong. Right? Vinyl cations aren't stable enough to be made. So we can't do SN1 with a vinyl halide because vinyl cations are bad. Technical term, bad. Vinyl cations are bad, okay? All right. Now let's go to aromatic halides. Right. So aromatic halides, right? Remember, this is an aromatic ring. Right. We talked about this is like a functional group. Right. No SN2. SN2, no. Because think about this ring. For me to do backside attack as a nucleophile, I have to go inside the ring, right? And I can't go inside the ring. It doesn't fit. It doesn't work. Okay, I didn't want to erase it. So, an impressive display, right? Right? So to get backside attack, you have to actually be inside the ring, right? You can't get inside the ring. Not gonna do it, right? And then for SN1, it's pretty much the same thing as the vinyl halide, right? If it leaves, you again make this, what's the equivalent to a vinyl cation, which is bad. So SN1 and SN2 reactions cannot happen at sp2 hybridized carbon. So that's the take home. sp2 carbons, no SN2 or SN1. So that's what ties all this together, right? This is sp2. These carbons here are sp2. So halides on sp2 hybridized carbons cannot do SN1 or SN2 reactions, right? Now the next thing is having double bonds around can affect whether a reaction can occur. So not having your halide on the double bond, but having your halide near the double bond, right? So allylic and benzoic halides can undergo SN1 reactions, even primary allylic and benzoic halides, right? So I have a halide here. It's clearly primary. I have an uncharged nucleophile. And I get this product. Right? So this is primary, but it's also allylic. So if you remember when we talked about alkenes, right? We said that this carbon here and here is the vinyl carbon, but the carbon right beside it is the allylic carbon. Right? Being at the allylic carbon allows you to do different reactions. Same way with an aromatic group. If you have an aromatic group, and you've got yourself some snazzy old uncharged nucleophile here, you'll still get your product. These are both going through SN1 reactions. Oh. Right here, this is called the benzoic position. Benzoic. It is the carbon bonded directly to an aromatic ring is benzoic. Now, I just went through all that time telling you that this never happens, right? But these being at the allylic or benzylic position makes the halide special. The resulting carbocations are more stable due to a phenomenon called resonance. Right? So, resonance is something you probably should have learned about in Gen Chem. Right? So resonance is a phenomenon where one structure can be represented by two different Lewis structures. Right? Now, first we got to talk about types of bonds. There are two types of, not bonds, electrons. There are two types of electrons. I'll turn up here. Alright, so I'm going to go over my other computer here. Right. There are two types of electrons. I'm going to draw a structure. Right. You have localized electrons. Localized electrons. These cannot move. Localized electrons can't move. These are typically sigma bonds. Right? These are your strong single bonds that can't move. And then you have what are called delocalized electrons. Delocalized electrons are electrons that can move. These are typically lone pairs and pi bonds. Right? So lone pairs, right? We got lone pairs, and we have pi bonds. Double bonds, carbon oxygen double bonds, carbon carbon double bonds. These are delocalized electrons. Right? All the resonance structure is it is one structure. It is the same molecule that can be represented by multiple different Lewis structures. So basically, the only difference is the location of delocalized electrons. So in the case of a carbocation, let's talk about drawing resonance structures here. Right? Oops, sorry, a little rogue there. Right? So basically, individual resonance structures are imaginary. They kind of seem imaginary, but they're not. Basically, they are an average of how the molecule behaves. And if you look at this entire average, you can figure out how the molecule behaves and how stable it can be. Right? Resonance structures really just help us think about molecules. A molecule is never one resonance structure. It is a conglomeration of all the resonance structures. Right? So, in your different resonance, so like I said before, resonance structures only differ based on the location of pi electrons, and the resonance structures don't have to be the same. So, I think it's easier to show this as opposed to talk about it. Right, so, let's go back to the example I had before. So we've got this guy, right? And I'm telling you, these electrons can leave. I can make this. Okay? Now, our cation is an empty orbital. Okay? So that empty orbital is sitting there, and adjacent to it, the next carbon over, there's a pi bond. The electrons in this pi bond can come over and fill that empty orbital. And when that happens, you get a different structure. Now my pi electrons are over here, and electrons left this carbon. Right? So when electrons leave, you end up getting another empty orbital. So effectively what I've done is move these delocalized pi electrons over to fill an empty hole. And that moves the hole, moves the cation, and generates my carbocation, and moves my double bond. Right? So these two structures here are resonance structures. It's the same molecule, just that the double bond has shifted and so has the cation. You've just moved where the charge is. Resonance structures allow molecules to be more stable because now, instead of this positive charge being stuck on only one carbon, it's now spread out to another carbon. Okay? So you've now spread that charge across all three of these carbons. So sometimes you'll see this drawn as that double bond moving back and forth really fast. It's in one particular place. And your positive charge is spread out over those three carbons as opposed to being stuck on one. Being able to spread that charge out allows the molecule to be more stable. Okay? You can do this with negative charges. So you have a negative charge. Right? Negative charges are too many electrons. So instead of having an arrow going to the negative charge, you move these electrons to push down and then push the electrons out. So now what I've done is I've now used these electrons here to make this pi bond and use these pi bond electrons right here to make this negative charge. And again, this goes back and forth. Right? It doesn't have to be a carbon double bond. It can be an oxygen double bond. I push electrons up, push that out. The only difference between these two is basically where the negative charge is. The negative charge is moved. I've moved these delocalized electrons here, and I moved those delocalized electrons there. But all of my bonds are still intact. All of my sigma bonds, all of my single bonds are still intact. Okay? You can do this with an aromatic ring. Let's say we have a positive charge by an aromatic ring. I can move my electrons out. Again, when we have a positive charge, you have to take electrons to that positive charge. Right, there you go, positive charge. Right, I can draw another resonance structure now because I have a positive charge beside a pi bond. Right, I can draw another one because I have a positive charge beside a pi bond. I'm going to go up this way because I think I'm in this corner over here. Well, I'm in this corner. So I don't know if you'll see it. Okay? So you can draw a resonance structure whenever you have a charge beside a pi bond. Right? You can also draw a resonance structure if you have a lone pair beside a pi bond. Now you're not dealing with charges. But I can come down and out. So basically, you treat a lone pair like a negative charge. It pushes electrons towards things. Right? But you have to keep track of your charges now. Your resonance structures have to all have the same charge. Just like your mechanisms, you can't destroy or make charge. So this is neutral. Right? Neutral. I held my hand up to the screen as if you were here. Yeah, that's gonna work. Right. So this structure is neutral. Your resonance structures all have to be neutral. But I push electrons out, so this becomes negative, and an electron with 3 bonds is positive. So this is a reasonable resonance structure, but you just have to keep track of your charges. Again, you don't have to have carbon. Okay, I can go nuts here. We'll go oxygen, it's not really nitrogen. So any atom with a lone pair, you can use for resonance. So nitrogen has a lone pair. So I can push down and out to that carbon there. Right, so I have nitrogen with 4 bonds is positive. Right, I push these electrons from being in a double bond to just being a negative charge. So I have a negative charge here and a positive charge there. Net, I'm neutral. But now what do I have? I have a negative charge beside pi bonds. So what can I do? I can do another resonance structure. I can push these electrons down and push these electrons out. So my last resonance structure, you'll notice I'm using these double-headed arrows. These are resonance arrows. These are the arrows you're supposed to use when you draw a resonance. We might not be very creative at naming stuff, but we are kind of arrow Nazis. That's organic chaos, right? So I have another resonance structure. So anytime you have lone pairs by pi bonds, or if you have charges by pi bonds, you can draw a resonance structure, either by pushing electrons towards the pi bond or taking electrons from the pi bond to the charge. The last thing is that whenever you have 2 pi bonds side by side, you can draw a resonance structure. Yeah, what is our bond? There we go. Right? So these electrons can go this way and push out. So this carbon on the end here, this guy right here, right? Electrons left it, electrons went away from it. So then it has a positive charge. These electrons that left went here to make a new double bond. So there's a new double bond there. And then that pushed these electrons here out to this carbon. I'll make it blue. Hi, I'm talking to myself. That's right.
You're fine.
And then I have a negative charge there. As the first, we just got interrupted by someone, freaked them out, me talking to myself. But probably calling campus police right now to say there's a crazy man in 304 while talking to himself. Right? So if I get arrested and I'm in class on Monday, I did it for you. All right? So electrons left here, positive charge. Electrons got pushed here, negative charge, net neutral. Now I could draw another resonance structure where I went the other way. Make that one blue. Draw another resonance structure where I go the other way, where I go this way and out. Right, in this case, blue dot lost electrons, electrons left it, right? And then red dot, electrons went to red dot gets a negative charge. But again, net neutral. All right, so some rules here. Resonance forms always must be a valid resonance structure. I mean, a valid Lewis structure. What that means is you have to always have an octet of electrons. Or you always have to have 8 electrons. And unless you have a cation, then you get to be short 2 electrons on a carbon. Right? Other good rules of thumb are, right, so electro, negative, atoms, like, negative charge. But hate positive charge. Right? So if you have this, you could draw this resonance structure, right, where these electrons came down, right? But now you have oxygen with a negative charge. So this is the most common resonance structure because carbon is less electronegative than oxygen. So carbon can better handle having a positive charge than oxygen can. Oxygen is really electronegative. It doesn't want to have a positive charge, right? But conversely, if you have this, right? This will be the most common resonance structure. Oops. Sorry. Because now you have a negative charge on the most electronegative element. Right? So these two things here, these two guys, are resonance contributors. Oh, that's right? Resonance contributors. So this resonance structure is best describes contributes the most to the resonance structure. So it is the most prevalent resonance contributor. Over here, this one being most common is the greatest contributor. So basically what I mean by the greatest resonance contributor is that guy best explains how the molecule behaves. Right? The other rule is that, the other good thing to remember here is that resonance leads to stability. The more resonance structures you have, the more stable you are. Right? So, if you have 2 resonance structures, you're more stable than if you have 1 resonance structure. If you have 8 resonance structures, you're more stable than if you have 7. Right? Oh, there's one more resonance structure rule I want to throw out here real quick. Okay, before we go on, before I totally drop the ball, I think we're like an hour 20 right now. We got a few more slides and then we'll be good. All right. Another thing is charges in resonance structures. Right? You would prefer to have a neutral. Right? Neutral resonance structures are better than charged resonance structures. Spelled right? No, that doesn't look right. Yeah. Hooked on Pahonics did not make West Virginia. There we go. Right? Neutral versus charged. Neutral is preferred. Right? If there are charges, it is best if they are close. Right? You don't want a lot of charge separation. You want your charges to be close. So for example, right, I can take these lone pairs, push them down, push that out. There's one resonance structure, right? Lone pairs come down, push out electrons. I can then draw a resonance structure where these electrons, now I add a charge beside a pi bond, and then those can come out. Oh, sorry, I flipped that number. Don't want to wait to be the other one. Whoop. Oh. Right? Right, this would be the best, the largest contributor because it has no charge, it's neutral. But now we have these two charge resonance structures. Here, these charges are closer than these charges, so this one would be preferred over this guy. Because the charges here are close as opposed to the charges having a great deal of separation. All right. So now we're going to go full circle here and get back to substitution reactions. Right? Since cations formed at benzylic and allylic positions have resonance, they're able to happen. Therefore, SN1 and SN2 reactions can occur. So we've got, let's say, a benzylic cation. Right, benzylic cation, it leaves. We now have a benzylic cation. Right, you're absolutely right. This is primary, but it's primary and it's benzylic. Right, and as soon as it becomes benzylic, this carbon right here isn't stuck with that positive charge. Through resonance, like we showed before, that positive charge is split up among all of these other carbons. So think of it kind of as like moving a couch, right? If you gotta move a couch by yourself, it's pretty hard. They're heavy, they're awkward, right? And you gotta like try to do this on your own. Right? Having a carbocation is kind of like a couch, right? Go home, pick up your couch, try to walk it around your room. It's not going to happen. It's a pain, right? It's really heavy. Oh my God, this sucks, right? That's the primary carbocation. Oh, so heavy. Carbon can't handle the weight of the carbocation. But when you have resonance, like here, right? Now, this carbon is not by itself. This carbon gets to spread the weight of that carbocation, gets to spread the instability of that carbocation across 1, 2, 3, 4 carbons, right? Now if you go home and you get 4 of your buddies and you promise them pizza and beer, they will pick up your couch and move it. With enough pizza and beer, they'll pick up your couch while you're sitting on it and move it, right? It's easier with a team, right? So benzylic, you have a team to move that carbocation around, as opposed to just being a primary carbocation that is not benzylic. There's no resonance. You can't make it because there's no way to move it around, right? But when you're benzylic, you can move that carbon around. You can move that charge around. Same way with an allylic carbocation. Right? This is going to have no reaction. Because as soon as you go to make a carbocation, it's primary. Can't do it. Not going to do it. That's my impression of Dana Carvey doing an impression of the first President Bush. Right? Now, as soon as it becomes allylic, you can get the product. Oops. You can get the product. And that's because electrons leave. You make this carbocation, but now this carbocation is not alone. You can move that carbocation, and now you spread that charge out over 1, 2 carbons. So resonance is the ability to move electrons move delocalized electrons to make other Lewis structures. Great. Now we're to the review phase here. SN2, right? So that's resonance. I'll give you some resonance problems on the homework. Might be a little more complicated than what I did. This is the gist of it. I need you to, for the test, or to give you a structure. I should tell you, draw all the resonance structures. You'd be like, all right, boss, I've got lone pairs here beside a carbocation. Those lone pairs can go towards that charge. Right? Keep track of all my charges. That's a plus. Terrible plus. Terrible. Or Charles Barkley. Terrible. Horrible. Right? Right? I can also do this resonance structure. Right? Pylon beside a charge. I go to the charge. Make that happen. Then next resonance structure, again, I have charge by cation. Sorry, I have charge by pi bonds. Bang. There you have it. So on an example, I could give you this structure and say, draw me all the resonance structures. And I'd expect you to be able to draw all the different resonance structures. Right, that's kind of the take. All right. Again, comparing SN1 and SN2, kind of the summary here. SN2, one-step mechanism. Nucleophile pushes out the leaving group. Right, nucleophile, so SN2. Let me keep track of these real quick. Right, one step. I didn't know what I was even trying to do, guys. All right. Nucleophile pushes out the leaving group. Bimolecular transition state, right? That means the concentration of the alkyl halide and the nucleophile matter to the rates. You have no carbocations. Right? There's no intermediates. It just pushes it out. No carbocations, no big deal. You need to use a strong charged nucleophile. So that's our metals, metal, lithium, or potassium typically, and let's cesium there. Cesium is my homeboy, right? And so you have metal OR, metal NHR, or metal NH2, or metal NR2. You've got metal and then sulfur, O8SR. Metal and alkyne. Metal and O. Metal and cyanide. Okay. And I'm a weirdo, I love the smell of copper cyanide. I once almost got gassed by an undergrad who quenched a sodium cyanide reaction with HCl, which makes hydrogen cyanide, which smells like almonds for a little while, and then when you stop smelling almonds, you die. And I was in my lab like, what's that smell? Man, I love it. That smells awesome. What is that? And somebody walked by, a guy who chews tobacco, because cyanide makes tobacco taste differently, and he's like, your lab kind of smells like cyanide. I went, oh, you're right. That is what it smelled like. And she had no idea what she had done. And was like, how much did you use? 2 equivalents? No idea how much. So we you shut down everything in the lab and ran out. It's like, you could kill us. And her eyes got real big. Really? And then she had to come to work for like 3 days and we thought she died. She didn't die. She's fine. She lives in North Carolina. She's okay. All right. So strong charged nucleophiles, things like this. I don't know if I have all of them, but you get the basic gist of it. Right? Polar aprotic solvent. right? So CHF, DMF, DMSO, and acetone. Right, those are all good. Remember, the rate goes methyl, faster than fast, methyl, then primary, then secondary, never tertiary, fast, slow, right? And reactions at chiral centers invert configuration. Right, so leaving group up, go, and then nucleophile goes to nucleophile back, leaving group back, nucleophile leads to nucleophile up. And then finally, SN1. So that is a two-step mechanism, right? Unimolecular. So SN1, two steps, right? Only concentration of halide matters. Whoa, almost fell down. Right? Carbocations are formed. So carbocation / rearrangements. You can do rearrangements, so heads up. You want to use polar protic solvents. So that is alcohols, amines, and thiols. Just think of sulfur as oxygen fat acid. They basically do all the same stuff, right? The only tertiary faster than secondary, right? Fast, slow. Primaries will work if allylic or benzoic. Right? So you have to have it by a double bond or by an aromatic ring, and it can be primary and work. But otherwise, primaries will not work. And then finally, if you have a chiral center, right, uncharged nucleophile, no charge, so under SN1 conditions, you will lose your stereochemistry. Peace out. No stereochemistry. And I feel like I've talked forever. I think I'm like an hour and a half in. You guys are probably all like planning to murder me now. So we're good. We're done. If you've asked about getting in the lecture, I'm trying to increase the enrollments now. But otherwise, I think we're good. So have a good weekend. Watch this by Monday because I'm just going to go right into eliminations. Right? So, all right, I'll see you Monday. I'm going to go watch Captain America. Woo!